Today let we learn about how to implement your simplified Boolean expressions using only NAND gates and NOR gates. Now, so in last session we learned about after minimizing, so how to implement your functions using AOI logic. So now why to convert into NAND NOR is, so since NAND and NOR are called as universal gates, because so we are going to implement any boolean functions or your basic logical gates using your only one type of ICs. So now these NAND and NOR gates are very easier to fabricate with electronic components, and these basic gates are implemented so using your a single type of gates instead of using three different ICs for implementing your function. So we are going to use only one type of IC, either a NAND gate or a NOR gate. So like that, so we can minimize your cost and it is more cost effective. So while we are going with your manufacturing your NAND and NOR, so instead of your and or, so in practical circuit only one type of gate is used for simplifying your hardware design, and which can reduce your power consumptions too, because these are operated with your less amount of voltages. So now how to implement your basic functions of your basic logical gates of your Boolean algebra using only NAND gates. Now we already learned so that NOT is always gives you the complement of its input. So y is equal to a bar. Now how this NAND gate is functioning like a NOT is by interconnecting the two inputs and connected to the common input variable, it can function like a NOT. So or else, so one of the input of your NAND is transferred with a logical one, it also function like a NOT. So how it is functioning like a NOT, because my output expression of NAND is equal to, with the two inputs, is equal to AB bar. So if the second input is also A, so then I'll obtain here A and of A. So A and of A whole bar. So A and of A using AND loss is A. So A bar. So like this you can construct or you can implement a NOT gate using only one NAND gate by interconnecting two input, or else, so one of the input if I transfer with a logical one, so then the B input is 1, so A and of 1 using your AND loss is A, so you can also implement your NOT function using only one NAND gate with always transferred the second input with logical one, and the first input is transferred with the input which you wanted to complement. So like this we are going to implement your NOT gate. So this is the most popular popularly we are going to use. So this type of your conversion by interconnecting the two inputs. Now, so how to implement a AND function? As we know, so your output of your NAND is nothing but complement of AND. Complement of AND is known as your NAND. Then if I complement the output of your NAND, so then I obtain the output of your this NOT gate is AB bar is the input, AB bar is the input, output of your NOT gate is bar. So one more bar will have, so due to this NOT gate. So now, so if you have a double bar, then double bars are cancelled, then we obtain your AB. Now I'm going to design the circuit with only using NAND gates by replacing your NOT with your NAND only, like this. So we are going to replace. So with the use of two NAND gates we can implement your AND function. In the same manner, a OR function is implemented using only NAND gates, because here AR of B is my output expression of your OR. So now if I do the double complementation, so then output may not change, so you obtain only AR of B. Using your De Morgan's theorem, so AR of B whole bar, I can write it as A bar and of B bar whole bar. Now here if I connect, so now I made this expression which is in completely in the form of your NAND. So if I connect the complemented inputs to a NAND gate, so it will give you the OR function. So now in order to do the complementation of your two inputs, I used your two NAND gates. The first NAND gate will complement your input, the second NAND gate complement your B input, and these complemented inputs if I transfer as the input to this NAND gate, so then our output will give you the functionality of OR. So now A bar is the input, first input, B bar is the second input, whole complement is the output of your third NAND gate. So which is equal to, now using your De Morgan's theorem, A and of B whole bar is equal to A or of A bar or of B bar. So now as inputs are complemented, so these two double complementations on your two inputs will give you the input which is uncomplemented. So A or of B. So like this we will implement using three number of NAND gates. A OR function is implemented. The same manner, so implementation of basic gates using your NOR gates. So now here by interconnecting the two inputs of your NOR gate together and connected to the common input variable, it can function like a NOT. So now A OR of A whole bar. What is A OR of A? This using OR laws, it is equal to A. So A bar. So only one gate we are going to use and connect your two inputs together, which will implement your NOT function, or else one of the input if you transfer with a logical 0, so then our output function of your NOR is A OR of 0 whole bar, which is equal to A OR of 0 using OR loss is A bar. So we can implement a complement of your input at the output of your NOR by transferring your one of the input with a logical 0. The other input is which you wanted to complement at the output is transferred with A. So like this also we will implement your NOT function. Now, so how to implement OR using only NOR is, so we learned NOR is nothing but complement of your OR. So now if I complement the output of your OR using a NOT gate, so then we obtain your OR function. So A OR of B whole bar is my input of this NOT gate and double A and bar is the output of your this NOT gate. So now these two bars are cancelled, then we obtain your OR function. And now we are replacing this NOT gate with only using NOR gate. So hence we obtain here the output of your these two NOR gates will implement output function of your OR gate. Next, how to implement AND gate using only NOR gate is, let I take the expression of your AND function which is AB, and now I'll apply double complementation on that, and then using your De Morgan's theorem. So first I will distribute this, so as A bar OR of B bar whole bar. So now we've made that expression completely into the form of your NOR function, but here we need to transfer the complemented inputs as the inputs to the NOR, so then it will implement your AND function. So hence, in order to complement your inputs, we use this first and second NOR gates, which will give you the complement of your A and B. Thereafter, you transfer those as the inputs of your third NOR gate. Now, output of this NOR gate, third NOR gate, is equal to A bar is the one input, B bar is the second input, whole bar. Now it is equal to A bar whole bar using De Morgan's theorem. This OR become and then B double bar. So these two double bars are cancelled, and then there is a product in between your A and B. So like this we are going to implement your function of AND using three number of NOR gates. Now how to implement your function which is AOI logic system completely into your NAND logic. So as here, so here we have converted your AND gate with the NAND gate by bubbling it the output. So which is AND inversion. So which will give you NAND. Now if I do the inputs which are bubbled and connected to the OR gate, it also implement your NAND function. So now using your De Morgan's theorem, x bar or of y bar or of z bar is equal to x, y, z whole bar. So like this, so we can have your NAND function, your bubbled or inverted input or can function like a NAND. So in the same manner, here now we were going to implement your function, how to implement your SOP expression completely into NAND logic. Now, so expression which is having two product terms are given, and now my minimal expression is AB or of CD. So hence in the first level we have a set of AND gates, in the second level you have a OR gate. Now in order to completely implement this with only NAND gates, so now every output of your AND gate is bubbled and every input of your OR gate is bubbled. So hence we bubbled your every output of AND, which makes with the NAND gate, and if you do the every input of your OR gate is bubbled, so this also replaced with the only NAND gate. Now we have to check for the inserted bubble compensation, as A double bar always equal to A. So hence here check for the inserted bubble compensation. If these are compensated, so no need to insert a NOT gate. If these are not compensated, insert a NOT gate onto that particular input line. So here, so these inserted bubbles at your output as well as inserted bubble at your input of your OR are compensated. Now in the next step, we were going to replace the inverted bubble input or your bubble input OR with your NAND logical symbol. Now, so let me observe. So the same functionality let me have like your AB or of CD from your SOP or AY logic system, which is only using your NAND gates. Are we going to get that or not? So here AB bar is the output of this first NAND gate. CD bar is the second NAND gate output. Let I complete this function f. F is equal to now. So AB bar is one of the input and of for the AND gate, and CD bar is another input. Output of this third AND gate will be giving you a complement of these two inputs. So now it becomes AB double bar and this AND become OR, so plus of CD double bar. So these two are cancelled. The same functionality what we obtained from AY logic, the same functionality is also obtained by replacing all these AND gates and OR gates with the only NAND gates. The same manner, here in another example, we have a simplified expression which is equal to with the three product terms xy bar plus x bar y and z. So now here if I draw the diagram, so then logical diagram of your SOP expression, I require two AND gates with one OR gate, and now so that OR gate output would generate your functionality f. So here xy bar is the first NAND gate inputs, x bar y is your second NAND gate, and z is your the one of the input of your OR gate. So f is equal to product of this first NAND gate will give you xy bar. So second NAND gate will give you x bar y. Next output of OR will give you summation of these product terms as xy bar plus x bar y plus z. Now, so how to replace this with your NAND is every output of your AND gates are bubbled and every input of your OR gate is bubbled. Now inserted bubble compensation I am checking here. First NAND gate bubble is compensated here with your one of the input of bubble of your OR gate, and here the second NAND gate bubble is compensated with this, but the third NAND gate third bubble of your OR gate is not compensated. Hence we inserted on the Z line with a NOT gate, or else you have to complement your Z bar. So if you are connecting a NOT gate on this line, if you are wanted to connect only Z, so then on this line you have to connect a NAND gate which can function like a NAND. So now our actual criteria here is to minimize your number of logical gates. So now in order to reduce that, so here let I just complement your variable z bar only. Okay, so now let me have this here. So here it will give you the product term of first NAND gate, which is xy bar whole bar, and second NAND gate output will give you x bar y whole bar, and this is the input for your third NAND gate, which is z bar. So now what will be the output of third NAND gate is equal to x y bar whole bar and of x bar y whole bar and of z bar and we have a double bar over there. So which is equal to x y bar double bar plus x bar y double bar plus z double bar. So which will give you x y bar, double bars are cancelled, then here, so this and is converted into or, so hence we have a sum term which is x bar y plus of z. So like this SOP is completely now it is converted into the, so if you are connecting a NOT gate here, so then here you should not take this as a Z bar, here it will be Z only. If it doesn't connect this, then you have to only take your, we have to complement your Z bar. Okay, so completely we have changed now. So your AOI logic system into your NAND. In the same manner, how to convert your function into NOR is, so your, by using your De Morgan's theorem, NOR is implemented by complementing its output of your OR. The same manner, if you connect your bubble input at the input of your AND gate, it also gives the NOR functionality. So now, if your function is in SPOS form, the minimal expression will be derived into POS forms. Now, upon getting that product of sum terms, so here the first array we have a set of OR gate. In the second array you have a AND gate which will do the product of these sum terms. Now, in order to implement a NOR implementation, every output of OR is bubbled and every input of your AND is bubbled, and thereafter check for your bubble compensation. If it is bubble compensated, then no need to put any NOT gate. If the bubble is not compensated, put a NOT gate or your inverse your variable. So now upon that, so replace this symbol of your inverted input AND with your NOR gate. So with that we can completely change the AOI logical diagram into your only using your NOR gates, which is called as NOR implementation. So like this we would convert your AOI logic system into NAND or your NOR logic system.